तो उससे बोल देना कि विड्रॉ कर ले फिर इसमें से ना। हाँ तो उसको बोल दो विड्रॉ कर लेगा, पॉइंट है नहीं। असल में एक दो लोग और थे वो भी बीच में, अब एग्ज़ाम के बाद आना शुरू किया तो क्या समझ में आना है फिर तो, बिकॉज ऑल द डिस्कशंस आर ऑल फॉलोइंग फ्रॉम द स्टार्ट। सो anyway, I guess you must have looked at the vorticity equation or the equation for mean vorticity. On Friday we will have that as a submission, the homework which was given. वो अपलोड कर दिया होमवर्क साइट पे? ठीक है, ये क्या हुआ, कोई बात नहीं। Okay, so I think we start now. कितने लोग हैं? Okay, so the equation which we said, equation for omega I prime, and for stationary flows, that means we did take the unsteady term out, it becomes mean of uj Did I write this equation in the last class or no? I am not sure if I did it. Now, whatever I am writing now is all on the right hand side, minus half. In the homework, you are supposed to derive this equation. It's actually quite straightforward because most of the terms, then we have plus looks like a pretty handful equation with all these terms. This is same as Lumley's text, the last expression on that bottom page. I've just copied it down. I'm going to number the terms so that, because we'll now see, now the whole analysis what we are trying to do. We did the same thing for the energy equation. We had the equation for kinetic energy fluctuations. We wrote the full equation. Then the next step is to estimate the order of magnitude of each of these terms. And then we keep only those terms which are retained when we do, which are, and we assume Reynolds number is large. So it turns out many terms have a very small order of magnitude. And then we try to see the balance of the remaining terms to try to understand the physics. As per this equation, when you do your CFD, etc., probably there will be very little role, or there will be no role. Because in the CFD, whichever model you follow, you will just solve the equations for those. And you are hardly going to ever solve the equation for omega I prime, omega I prime. So the whole purpose of doing this is only to understand the physics. Okay? And that's why we are going through this. This is a course of physics in turbulence. So we are trying to understand the physics of the various terms. Now, does anyone remember what happened to the energy, turbulent kinetic energy equation? Finally, after all the order of magnitudes, etc., what form did it take? It took a form, I think we did it a while back and I don't expect you to remember, but if you turn through your notes, we got the form production is equal to dissipation. अब याद आ गया, I also knew, मेरे साथ भी यही होता है. So minus ui prime uj prime d mean of ui by dxj, that was the production, is equal to nu times du prime by dxj, du prime by dxj. This is what that balance became. Now we are trying to look for a similar balance in this equation. Is that clear? So maybe let's try to write the philosophy down, because that has not been written. So we are trying to do an order of magnitude analysis of various terms to see which terms are important in the limit REL tends to infinity or is large. Similar exercise for turbulent kinetic energy equation led to production is equal to dissipation, P was equal to minus of ui prime uj prime d mean of ui by dxj, and epsilon was equal to nu times So, now the third thing which books don't talk about, but if we look at the overall form of the equation, what we find is that all equations for all quantities have a same pattern. For example, the Navier-Stokes equation is partial ui by partial t plus uj dui by dxj is equal to some pressure term or other terms which are there, a source term, a transport term, and a dissipation term. Now, other than the dissipation term, whichever terms come on the right hand side, we try to look at their nature. Some of them we call them as source term, and the others we call them as transport terms. Particularly the transport terms are the ones which some of you, which we saw in the exam also, are the ones which by using the Gauss's theorem turn out to be boundary terms, and therefore if the term is on the boundary is equal to 0, then it leads to that the term will basically be redistributing that quantity within that volume. And these we are called redistribution or transport terms. And this happened in mean velocity, this happened in mean vorticity, not only instantaneous velocity, instantaneous vorticity, mean vorticity had a similar form, but mean ui was replaced, uj dui by dxj was replaced by mean of dui by dx, mean of ui times dui by dxj, and then of course there was there's a quadratic term and a second term came there, which was the Reynolds stress term when you took the mean. But again, so on the left hand side the trend is very similar, at least 2 and a viscous term. So this is. Now here I'm not sure this epsilon whether it had a negative or not. I think it may have had. I'll just write it, but please check it whether the negative was there in the P is equal to E term. नहीं था? Okay. Just check कर लेना, मतलब I'm not sure. Okay, so I'll just leave it, I'll put a question mark here. So the third term point which I was making, let me write that down, that equations for all quantities, be it ui, mean of ui, omega I, mean of omega I, turbulent kinetic energy K, omega I, or these are the equations we have derived so far in this course. In a nutshell, maybe there may have been more. ui, mean of ui, omega I, the vorticity, mean of omega I, turbulent kinetic energy, mean kinetic energy, turbulent kinetic energy, mean enstrophy, and fluctuating enstrophy. So these are the equations we have derived, and equations of all these quantities have the form if equation is for phi, then they have the form partial phi by partial t plus uj production term plus transport plus viscous. Now, how do we define the transport terms? The transport terms, or what did we call it? Redistribution terms. Transport terms are have a d by dxj. So, on application of Gauss theorem, they on the volume they become NJDA, and if the bracket quantity is equal to 0 on the boundary, then the d by dxj term redistributes the bracketed term in the volume. हाँ एक मिनट, क्या चीज़ ऊपर करना है, ठीक है. I was just writing this. I think often I realized in my notes, I say a lot of things, I don't write them, and they don't go in the notes.
Here is a copy of the homework. You have written epsilon ij as just the two new thing, and you have written on the RHS as minus epsilon ij. So this is like, this doesn't have a negative sign.
It doesn't have, that's okay. That's fine, thanks. Okay. So this is the philosophy of what we are doing. The first 2 points explain why we are analyzing the equation, what we will do. And the third point is a general point, which is again something which is physical, and actually as I said, there's one of the friends of mine who also works in turbulence, actually is more known, more than his turbulence, for his work in anthropology. There's a particular paper he wrote in anthropology, how societies evolve. And there he used this sort of, it's not exactly this logic, but he used this sort of a logic to derive an equation for the evolution of societies. That the rate of change plus the whatever is changing due to time will be equal to production plus redistribution plus the dissipation. So he worked and making some models, he was able to predict certain things in this evolution of society. So, some of you will probably be going in the modeling of stock market. So, maybe you can think of using an equation like this to try to predict. So, this is just sort of trying to get you to see how these things could be used in different fields also. Okay. So, now if you have written all this, let me number these terms so that we will look at, so this term we will call as the left hand side, the left hand side term. The first term here, I am calling it as T1. Okay, I am just giving a number because so that we can tackle these things. Second term is T2. We will look at the physical meaning and all of T4, T5, T6, T7. So, T stands for term. I am not using transport or anything here. I have just numbered the terms 1 to 7 and there is a left hand side. Let us just call it left hand side. So, now let us try to start. T1. T1 is basically something like the production term. We have d omega I by dxj acting on uj prime ui omega prime. It is not on omega prime. So, no T1 एक मिनट रुकिए मैंने क्या किया है, did I miss out something? Okay, yeah. So T1, that's okay. So let me now give you the physical. First, I will talk of the physics of all these terms. So T1 is the production of omega I prime, and basically it's the exchange of vorticity and between omega I prime and omega I. So this is exactly like this term. It occurs in both the mean equation as well as the fluctuating equation, and this is like of course here in the kinetic energy equation we got ui prime uj prime. We are not getting omega I prime omega j prime. It is ui prime omega j prime or the other way around. So this is what the first term is. So once you have written that down, I will go back to the equation again. Maybe I could have written the equation on the board. If you want, I can do that. T2 term, okay, can I move on? The term T2 is half of d by dxj of uj prime omega I prime omega I prime. So this is the transport of mean square vorticity by the turbulent velocity fluctuations. Transport of omega j prime by uj prime. Okay, so that is T2. Let me write that now. So T2 is the transport of mean square turbulent vorticity by turbulent velocity fluctuations. Okay. Now, the third term, T3, this is, I'll just write the term here, omega I prime, omega ij prime, Sij prime. I'll not go up now. This is production of see, now you realize why do we call it production? The other term we call transport because there was a gradient. In T3, there is no gradient. It is basically, this is the term. Now onwards, instead of going up, I will write the term here. So this term is production of mean square vorticity fluctuations by turbulent viscosity, or basically by turbulent viscosity, or you can also call it by the fluctuating strain rate. The fluctuating strain rates are what cause what we effectively call them as turbulent viscosity. So this production by the fluctuating strain rate. So this term is the third term. Because fluctuating strain rate, turbulent viscosity, C U prime L लिखते हैं तो which is basically coming from the fluctuating strain rate. The turbulent viscosity जो है उसको मतलब that comes essentially from the fluctuating strain rate.
So
Nu T हम
that comes
तो
from fluctuating.
U prime L लिखते हैं तो U prime times मतलब nu T will write it. So this is how it is explained. Now T4, which was omega I prime, omega j prime, mean of Sij. This term is the production or removal of turbulent vorticity caused by squeezing or extension of vorticity fluctuations by mean strain rate. See, basically there is a mean strain rate. Mean strain rate will tend to either pull or squeeze the vorticity fluctuations, and that is basically the term which this represents. That mean strain rate acting on vorticity fluctuations and the average of that. So this is T4. T5 term, which was mean of omega j prime Sij prime. This term is a mixed production term and also occurs in omega I omega j equation with the same sign. And this represents stretching of fluctuating vorticity by fluctuating strain rate and causes the same effect in mean of omega I and omega I prime equations. Or actually it should be mean, same effect on mean of, ये इसको मैं change कर देता हूँ, let me just change this. The last part I am changing, causes the same effect in, I'll put it in words, mean enstrophy and fluctuating enstrophy equations. T6, which is nu times d2 by dxj of half of omega I prime. This is the viscous transport of omega I prime, and T7, which is minus nu times d omega I prime by dxj. This is the viscous dissipation of the enstrophy. So these are the various terms we have given the sort of interpretation of all of these. Of course, the interpretation in a lot of ways, you just renamed it as something else. You may think of it as just, but we are trying to sort of understand. Now let's look at the order of magnitudes of all these. So next step will be, let me complete this, orders of magnitude of various terms. Yeah, और ऊपर, ठीक है. It comes in both the equations, omega I होगा ये. Okay, thanks. We are thankful that we are not looking at omega I omega j equation. Otherwise it would be even.
Can you explain T1 again?
T1. T1 is basically, in the turbulent kinetic energy equation, you get a term ui prime uj prime sij. So that tells you what we say, that this is uj prime is being acted upon by ui prime because of the mean strain rate. Now similar to this term is equal to, so let me write the T1 term here before T1 was minus of uj prime omega I prime times d mean of omega I by dxj. So this term is very similar to this term here. That is, this Sij is dui by dxj. So here it is d omega I by dxj, uj prime omega I prime. So that's why we call it that it's a production of, you can call it omega I prime. But because this is the equation for omega I prime, so this represents production, it's a positive term. And it represents how, because the equation is for omega I prime, how the production of this takes place because of the role of interaction between velocity and vorticity, on which the gradient of mean vorticity is acting. So we have tried to give the meaning just based on the kinetic energy equation. And actually what we will find out is most of these terms will be very small, just as we got P is equal to E equation we will get a similar equation when we complete the order of magnitude analysis.
So, do we have definitions of like stringent equivalence, but for
Vorticity,
vorticity?
we don't.
Because it's occurring
It is basically, it's occurring in this equation, but it will turn out the order of magnitude of this term will be small. So eventually, when we do the balance, this will go away. So that's why we don't sort of dwell too much into this. So now we have to do the order of magnitude of various terms. So let's look at a turbulent flow where Re sub L is large. Now in this flow, we have already shown a Sij prime is much bigger than the mean strain rate. This has already been shown. And also we have shown that, and this is order of magnitude, maybe we can write it, order of magnitude of omega I prime is much greater than order of magnitude of mean omega. So this we have shown. We have also shown these terms occurred in the turbulent kinetic energy equation. Mean of Sij prime, this was of the order of what we called as U prime RMS upon lambda whole square, and we have shown mean of Sij is of the order of U prime RMS upon L whole square. We also showed mean of omega ij this is of the order of U prime RMS upon L whole square. Basically, Sij and omega ij have the same order because both of them follow from mean velocity gradient. Okay. Now, there is this term mean of omega I prime. And we want to show the order of this. So, to show the order of this, what we do is we write omega I prime, this is equal to 2 times Rij prime. Now, to get to this, you will have to expand omega I. We have done this expression is equal to epsilon ij k r kj. The second omega I, you will have to write it as epsilon I Lm r Lm or RML. It's the second order. And then the two epsilons which are there, I is common. So they will become a product of two delta functions. And then when you expand the two Rij's, and it will become Rij. One of them will have a negative sign, but then it will also have one of the R's with an opposite sign. So because Ri is antisymmetric, when you flip that, it will become Rij, and you will get this form. So this you can try it out with just a 2-minute exercise or maybe 5-minute exercise, and you get it in this form. For this, we just need the antisymmetric nature of Rij. That is what is needed, and also we need the relation omega I is equal to epsilon ijk Rij, or yeah. So with those two relations, we can get this. So this you can get it. So now what we can show is, if I look at du dui prime by dxj times duj prime by dxi, this is equal to Sij prime plus Rij prime times Sij prime minus Rij prime, and this is equal to क्या हो रहा है बाहर? The cross terms will go away, and then we have d, so this is there, and we have d2 this will become equal to so this equation, using this you will be able to get this, and then the reason why we are doing this is we already know Sij prime, Sij prime, this is of order u prime RMS upon lambda whole square, and d2 of ui prime uj prime on dxi dxj, this is of order u prime RMS square upon L square. So if we look at this equation, this term is of order u prime RMS square upon lambda square, and the left hand side is of order u prime RMS square upon L square. Now in the limits when Reynolds number is large, this order is very small. So that means this will almost become 0. So what you get is Rij prime is of the order of Sij prime, Sij prime. And Rij prime we showed earlier here is of the order of omega I prime, omega I prime. So let me write all the arguments. So this implies from A, mean of Sij prime is equal to Rij prime, because LHS is very small, and other term what we wrote was omega I prime was equal to 2 times Rij prime. This implies that order of omega I prime is of the order of Sij prime, and this is equal to u prime RMS upon lambda whole square. And this actually, you could have said, maybe I could have started put omega I is of the order of u prime RMS upon lambda. So omega I prime will be u prime RMS upon lambda whole square. But that argument has a slight this thing because it's a summation, and so there may be some issues. So we write it like this, and we've sort of shown it directly. See, this part, to write this, I will need this expression here. That's why I've derived this part. This will be needed to get to this form. That d2 ui prime uj prime by dxi dxj is equal to this. Okay? Okay? So now from here we make some physical conclusions also. So what we get is omega I prime is of the order is equal to 2 times Sij prime. This is what we get, and order of magnitude of omega I prime is equal to u prime RMS upon lambda. And what we also know is, so this tells us if the flow is turbulent, the rotational, this Taylor scale is important. So therefore, omega I prime is something which cannot be neglected in turbulent flows. In turbulent flows, omega I prime will always be significant, so turbulence is rotational. And the second thing we can show is, or we know dissipation is equal to 2 nu Sij prime. So from above what we get is dissipation can be written as nu times omega I prime. So dissipation of turbulence is associated with vorticity fluctuations. So we have shown directly that dissipation is basically directly related to the fluctuating enstrophy. So if vorticity fluctuations are important, that is where the scale at which dissipation will take place. Okay, this is what we are showing here. Next, today I think let's I'll now write the budget of each of these terms, and I'll probably go another 10 minutes or so. I hope किसी क्लास तो नहीं है 1 बजे, थोड़ा रुक जाना है ना, ठीक है. लंच भी 2 बजे तक तो मिलता है इन हॉस्टल्स, एटलीस्ट दोज आर इन हॉस्टल. जो खत्म हो जाते हैं यार, ऐसे तो नहीं खत्म होगा, इतना तो बुरा हाल नहीं होना चाहिए IIT का कि हॉस्टल में बजट क्या खत्म हो जाता है 1:30 के बाद. ठीक है, चलो. तो शोर मचाना चाहिए कि जब टाइम 2 बजे तक का होता है, तो देन हाउ कैन दे, मतलब है तो और बना के दो. So now we have to estimate, to do this vorticity budget, we have to estimate terms like uj prime, omega I prime, omega j prime, Sij prime, because here these terms may be non-zero because of their correlations of different quantities, not the same quantity. So what have we again earlier shown? We showed again, this must be, we have shown this. Sorry about this, ये बार बार क्यों हो जाता है ये. अर्ली शून्य हुआ क्या, ये पता नहीं कहाँ से आ गया। ui prime omega j prime is of the order of u prime rms square, दोबारा करने दो। Yeah. You have to leave. अच्छा ठीक है, तो ये फिर नहीं तो एक काम करते हैं, लेट्स जस्ट सी बिकॉज दिस विल बी अदरवाइज डिफिकल्ट टू। पूछ लोगे, यू आर श्योर? मतलब आई डोंट वांट यू टू मिस आउट, मतलब नहीं होगा, ठीक है प्लीज। ओके, सो विल ओमेगा जे प्राइम एस आई जे प्राइम was equal to order of magnitude of u prime RMS square upon L square. So these were already done, and then we have, now let's look at this term omega I prime omega j prime, and there is another term uj prime omega I prime omega I prime. Now here in this term omega I prime omega I j prime, the diagonal components are of order u prime RMS upon lambda whole square, because we just have sort of shown that. The off diagonal components are non-zero because of mean Sij, and mean of Sij is of order u prime RMS upon L. So we have omega prime which is of order u prime RMS upon L, and mean of Sij which is of order of this is upon lambda and u prime RMS upon L. These two terms have different frequencies. This is the frequency of omega prime, and the frequency of the mean strain rate is something like u prime RMS upon L. So the effect of mean Sij is proportional to the time scale ratio lambda upon u prime RMS divided by L upon u prime RMS. This is equal to lambda upon L. So the off diagonal terms of omega I prime, they are proportional. There is a ratio of lambda by L which comes in. So therefore, omega I prime omega j prime, this can be written as u prime RMS upon lambda whole square, which is what we would have expected. Now the diagonal terms are directly correlated, but the off diagonal terms have a lambda by L which will come in. So in a general way I could have expanded this, written as diagonal terms will be just coefficient A, and the off diagonal terms I will put lambda by L. So in a general way I am writing it like this. Okay. So this is what is omega I prime omega j prime, which looks like this. And if we look at the term which will come in will be omega I prime omega j prime mean of Sij. So this will become equal to u prime RMS upon lambda whole square a times delta ij Sij plus bij lambda by L mean of Sij. Now this becomes Sii, which is equal to 0. So therefore, what we are left with is omega I prime omega j prime is equal to u prime RMS square upon lambda square times bij lambda by L mean of Sij, and the order of omega I prime omega j prime, this becomes equal to u prime RMS square upon lambda square times lambda by L times u prime RMS upon L. मैंने थोड़ा जल्दी किया तो आई विल एक्सप्लेन इट. फर्स्ट यू कैन राइट इट डाउन, पहले सब लिख लो फिर मैं एक्सप्लेन करता हूँ. Yeah.
So you wrote that mean of omega I prime for the mean of omega I prime omega j prime, like it's above. So the
Also, no times Sij यहाँ एक मिनट तो Sij एक Sij लिखना भूल गया मैं यहाँ. हाँ अब बोलो.
the diagonal term of
हाँ.
components are of order u prime RMS by L whole square. But so like earlier you had written that
नहीं बाय L का लिखा है मैंने, एक मिनट गलत तो नहीं लिख दिया मैंने, लैम्डा ही लिखा है. कहाँ पे L का एक L लिखा था पर गलती से किया था, उसको लैम्डा कर दिया था. एक मैंने L गलत लिख दिया था, मे भी तुमने वो L को मैंने फिर लैम्डा किया था काट के. हाँ. ये यहाँ पे ना आई मिस्ड फर्स्ट रोट दिस इज L एंड देन आई चेंज इट टू लैम्डा, so I made a mistake. So here see basically what one is getting is order of, and यहाँ पे भी Sij होना चाहिए था. So what we say is that the diagonal components, they are of order u prime square upon square upon lambda square, and then when we multiply it by Sij and we write it in this form, then this becomes equal to Sii, which becomes 0. So the diagonal terms become 0. In the off diagonal term there is a lambda by L which comes in the scaling, and all the A and B's are of order 1. So therefore, when I write omega I prime omega j prime mean of Sij, which is a term in my equation, that will become u prime square over lambda square times, now this Bij is of order 1, lambda by L comes in as a correlation coefficient, and mean of Sij becomes u prime RMS square upon L.
Sir, the first step that you have wrote A del ij plus Bij del lambda by L plus so on. So how we got this?
No, this is basically, this is combining the two equations कि एक तो diagonal terms थी, एक non diagonal terms थी. So diagonal terms के लिए I write delta ij, and non diagonal terms के लिए it will just some tensor notation, but there I put lambda by L. Because so that I have explained that because the off diagonal terms are that term like omega 1 prime omega 2 prime will only come because of the production by the mean velocity gradient. So because there is an interaction of mean velocity and a fluctuating vorticity, so the correlation coefficient of lambda by L comes in. That is what the whole argument has gone on. Okay. So now this is what we have for this term. So now also there's one more term. The final order of magnitudes we'll do tomorrow. But if we look at the transport term, there was one more term which I had written, d by dxj of uj prime omega I prime omega I prime. This was the term written here on the second side. So this can be written as uj prime d by dxj of this part is coming because of continuity equation. I can take the duj by dx, I can first take the derivative inside and then duj prime by dxj is 0. So therefore uj can come out of that. It becomes d by dxj of uj prime omega I prime. But because duj prime by dxj is 0, I can pull it out. So it becomes uj prime d by dxj of omega I prime. And this term now, this can be written as equal to, now the order of magnitude of this will be uj prime, so see d by uj prime will become u prime RMS, d by dxj will become L, and then we have d by dxj of omega I prime. So this becomes equal to u prime RMS upon lambda whole square. So this total term becomes equal to u prime RMS whole cube upon lambda square. So now, what I'm going to do in the next class is, having looked at all these orders, we will go to T1, T2, T3, T4, T5, T6 and write all the order of magnitudes of all those terms from T1 to T7 and the left hand side, and then show that only 2 of them stay. There's one term in particular which you will note which comes in the equation, which is T7. Here now we are taking the derivative of vorticity. Now actually we do not know the length scale here. Just as when we did dui by dxj, or the vorticity term came, there we did not know the right length scale. We know the scale of omega I prime, but because it's a small quantity being differentiated, its length scale we don't know. So we will keep this term as an unknown and match it with whatever stays to get the order of magnitude. And then once we know the order of magnitude, we can get the order of magnitude of d omega I by dxj. What is the length scale there? Okay. So we'll continue from this. And I think tomorrow this whole discussion on omega I prime will end, which has been going on now for 2-3 lectures. And also I think the problem has come because of the breaks. Had this continued over 2 or 3 lectures, we would have finished it. It would not have looked that remote. But because the breaks came in, there was an exam, and then one day I could not take the class. But tomorrow we are definitely going to finish this. Okay? I don't know if you are enjoying this or if you find it drudgery. But एक चीज है कि एग्जाम की ज़्यादा फिक्र मत करो. We'll do things, we'll discuss what to do, and I want you to just enjoy the course. Just try to understand how things are going on, and
टाइम को लैम्डा से कर रहे हैं, हलेगा वही किया है. सो व्हाई वी आर टेकिंग एल